In this session, we'll see different examples to understand the basic concepts of Verilog. First of all, I would like to give an example on printing a hello world in Verilog. So let's start creating a project. So I'm creating a project. I'm naming it as hello world. I'm creating at this directory. So it is already creating a subdirectory based on my project hello world. So all the files like simulation files, synthesis files, implementation files, bit files, everything will store in this subdirectory. Next, I want to create an RTL project. So I'm selecting RTL. Since I don't have any files, since I don't have any source files, I'm creating new file, which is a Verilog language. The file name, let's say, the file name will be the module name. So let's say I want to create a module called hello. See, the hello.v module has already created. Now next, I don't need any constant file for this because I don't want to do implementation. I just want to do a simulation. So I'm clicking next. I want to select a board. In this course, we are using a board called JetBoard. Selecting it. Next. So this is the summary. I created an RTL project named Hello World and I added one source file and there is no constraint file. So I'm finishing it. Now it is asking whether you have definition of module, like you have input and output ports. As of now, I don't have any inputs and output ports. I am clicking OK. So it will give a warning that you don't have any, the module definition has not been changed, and are you sure you want to use these values? Yes. So see, the design source has already been created with hello.v. So double click on this, it will open a window. Here you can write your code. So the time scale is already by default, the Vivado has 1 nanosecond by 1 picosecond time scale. And the double slash, this we already know, right? This is a comment. So all these things are comment. You can hide these comments and start writing your code here. The Verilog HDL already starts with module and ends with end module, we have already learned. So in this particular case, I don't have any ports. So I'm removing this port definition and I'm directly keeping hello. So my task is to display hello world, right? So what I need to do, I need to write initial, then I'll use a display function, display. I want to display hello world, right? See, there is a syntax error. This is because this telling initial, the spelling of initial is wrong, is a unknown type. So correct it, initial. Now there is no syntax error. Let's run this program, save it, and run simulation, behavioral simulation. So it is compiling and it is running the code. Once the simulation is done, it gives the output here. See, the hello world is printed, right? So this is the basic program of Verilog. In the next program, I will explain how to use the operators that are available in Verilog. Like we have three different operators: unary, binary, and ternary. I will explain all the three different operators. So let's create a new project. Project, new, again next, to create a project on operators in Verilog. Next, this is an RTL project. Next, I want to create my own source file. So I'm writing operators, operators. Okay. Next, next, select the board. Next, and finish. So it is asking whether should I close the hello world program or not. Yeah, I want to close it. So yes. So now a new window is opened and it is asking again to define the module inputs and outputs. I don't have any inputs and outputs. I am clicking OK. Yes. So let's write the code for operators. Delete this semicolon. Now let's take a register A comma B. So I want to use an operator called unary operator. In unary operator, there will be only one operand. Here I want to perform B is equal to not of A. So let's see how to do that. Initial. Since we are using data flow modeling, we have to use this initial all the time. Initial B is equals to not of A. Done. But you want to define what is A, right? So I am defining initial A is equals to, let's say I want to define one tick binary of 0. You remember, right? In order to define binary numbers, you can define like this: how many bit binary and what is the format, whether it is binary or hexa or octal, everything you can define here. Right now I am defining one tick binary 0, and then I am assigning B is equals to not of A. Let's display these two things: initial dollar display. What I want to display is the value of A comma B are percentage. Since they are binary, I am using percentage B comma A comma B, and with semicolon. See, there is an error here. Error, syntax error near value. I haven't opened the quotation. So now you can see there is a change in color. So this is a string which is going to be print in the message window, TCL console window. So let's run this, save it, and run the behavioral simulation. Let's see the output. See, in the simulation window also you can see the output. Since we have given A is equal to 0, the B is 1, not of A is performing, right? Here also you can see the values. The value of A comma B are 0 comma 1. Now let's see how to use the binary operator. For binary operator, you need two operands. So I am taking one more extra register C, in which first I will do the operation of initial C is equals to A and B. So I am assigning A to 0 and B is already converted to 1 because B is equal to end of not of A, and C will be A and B. So let's see what happens. I am printing the values of A, B and C, comma B, comma C, right? Save it and reload the simulation. See, the value of A, B, C are A is equal to 0, B is equal to 1 and C is equal to 0 because 0 and 1 is 0. The same thing you can see in simulation window. See, only A and B are coming. Why not C is coming? C is coming here, but it was not added to this window. So what you need to do, right click here and add the C waveform to wave window. Now C is also coming, but it is not showing. In order to show it, you need to run the simulation again. See, now C value is also appearing in the simulation window. The third operator is ternary operator. Let's see how to use the ternary operator. I am taking one more variable called D, and I will perform ternary operation. If you remember the syntax of ternary operation, it is like this: D is equal to A and questioning whether A is equal to 1 or 0. If it is 1, then execute B or else execute C. Right? What it does is it will check if A is equal to 1 or 0. If A is equal to 1, then it will execute this statement. If A is equal to false or 0, then it will execute this statement. So let's print those values. Let's take comma, comma, percentage B, A, B, C, and D. So what will be the output? Since A is equal to 0, the B statement won't execute, the C statement will execute. What is the output of C? We already know C is equal to 0. Let's see, it will be 0 or not, the D value. I haven't written D here, so I can cancel the simulation. Right, A, B, C, D. Save it again, and then run it. Yes, the value of A, B, C, and D are 0, 1, 0, 1. Let's try with different value of A and we'll see the output will change or not. So what happens now? If A is equal to 1, then it will execute statement of B. Again, B is equal to 1, right? So I don't want to get D value as 0. So I want to C here and B here. Even C will also be 0, right? Because one of the input is 0. So I'm putting A here directly. If A is equal to 1, put the value of A into D, and if A is equal to 0, put the value of B into D. Let's see whether it is true or not. This is fun, right? I mean, you can do a lot of things using different operators in Verilog. You can play with the tool. It is very simple and it is very easy also. See, it is done. The value of A, B, C, D are, since A is equal to 1, directly 1, B is not of A, which is 0, and C is A dot B, which is again 0, and D, we used a ternary operator, which is asking whether A is true or false. If A is true, put the value of this A inside D, so it is going as 1. So this is an example of different operators that are available in Verilog. In the next example, I want to show how to use different data types that are available in Verilog. Like we'll use the register. We are already start using the register data type, but we'll use the vectors, how to use the register vectors in the next example. So let's create a project, new project. Again, same steps you need to follow. Project name is data types, data types. Next, it is an RTL project. Create a file. I want to create vectors in data types. Data types. Okay. Next, I don't need constraint file. Next, the board. Select the board, jet board. Next, and finish. You like to close? Yes. Since we have added some configuration to the wave window, it is asking whether should I save it or not. Right now I don't want to save it, so discard. Again, I don't have any inputs and outputs for this module, so I'm clicking OK. Yes. Double click this, minimize this. So in vector, let's take a vector like this. You remember the syntax of vector? It will be let's say I want to define a vector of 256 bit. So it will be 255 down to 0. My vector name is data, let's say, and I want to catch some of the byte data from that vector of 256 bit. So I'm creating a byte of width, which is a 8 bit. I'm calling it byte 1. Okay. Now what I want to say is I want to initialize this vector with some value. Initialize the vector data is equals to, let's say, any value 3, 2, 1. See, here I am not defining what is the format of this data, so it will automatically take it as a decimal value 3, 2, 1. Now I want to initial. If you don't want to write initial all the time, I already told, if you want to write multiple lines in initial, what you need to do is write begin, and then it is always good practice to start with tab so that it is easy to identify. Initial begin. What I want to do is I want to catch the first byte of the data register. So how to do that? Byte 1 is equals to data of 7 down to 0. So I am catching the last 8 bits of the data into byte 1. Semicolon. Then shift tab. Now these two statements will execute in the initial block. So let's save the code and run it. See, this is the output, right? The byte 1 is 41, which is very confusing, right? Because you want to print a decimal number in binary format. It's very, very big number. You can see all our zeros are appearing. You cannot even see what is the data. The 141, it was connected into 141. So what I will do is I will convert these into binary, no, decimal. So how to do that? Right click here and go to radix, change from default to unsigned decimal. Now the byte is changed to unsigned decimal. Same thing, do this data also to unsigned decimal. See, we have assigned 321 to the data. So that 321 came, and from this the first 8 bits is 65. The first 8 bit value is 65 in this 321. It is confusing, right? So let's take a small value so it will be clear for us. Let's take only 16-bit data, and we will define data in hexadecimal format. So the 16-bit data in hexadecimal format is AB, let's say, or some numbers will use 7 and 5. And we forgot to display this, so we'll use the display function. Display the data comma byte, or what kind of format we'll use? We'll use hexadecimal format. For hexadecimal format, you need to use %h, comma data, comma byte. Let's see what happens. I saved it and I'm relaunching the simulation. The data comma byte are 0075 and 7 comma 5. This is what we want, right? We have defined a 16-bit vector of data and then we are calling first two vectors. So let's say 65765. See what happens. It is giving a warning because 16-bit cannot be more than this. So creating AB, one more data. See whether AB is copied to this or not. Yes, AB is copied to byte 1. So let's take one more example where I want to assign this data using a for loop. So to do that, I need one more integer, let's say j. Taking an integer j, and I'm using a for loop in the initial block for j is equal to 0, j less than 1, j less than 2, let's say, and j plus plus. J is equal to j plus 1. And then begin. In begin, I'm taking one more variable byte. And I'm assigning byte is equal to data of j into 8 plus 8. You remember the syntax, right? You're calling a starting value incrementing to 8 bits. Semicolon. I want to display byte 1, comma byte also. Let's see what happens. See, there is an error, syntax error, because we have opened the begin, but we haven't closed it. So I'm closing this begin and end. Now the error is gone. Save it and run the simulation. See, it has printed 2 lines because we are running the for loop for 2 times. The first line, the data is 0, 0 AB, and we haven't given percentage h for this, right? So that's why it was wrong. Percentage h. Let's run again. Now see, the data is 0, 0 AB. In the first loop, when j is equals to 1, it has taken AB into byte, that was printed as AB. In the second loop, when j is equals to 2, it has taken these 2 bits, 00, and printed into byte. This is clear? Yes. Now, let's take an example where we want to see the functionality of system test function like dot time. This functionality is very useful to see the time of simulation that is taking. Let's create a project, new project. In this particular case, I want to use the system test function dot time to display the time of the simulation. For this, I want to take an example in which I will convert the real numbers into an integers. So the project name, I want to keep it as real to integer R2I, and it is an RTL project, and I want to create a project which is real to integer, and next, I don't need constraint. I'm selecting Jetboard and click next and finish. So I don't have any inputs. I'm clicking OK and yes. Now let's write the code. I'm removing the port declaration and I'm directly calling a real data type. Let's say the data type is pi. I want to initialize the data type. Initial, begin, and Let's say the value of pi is 3.14. I want to display that pi value. Display the value of pi is percentage f, since it is a floating point number, comma, the value of pi. That's it. I'm ending this initial statement. Now I want to store this pi value into an integer. Let's define an integer I. So again, initial, begin, I is equals to pi. So let's see what happens. As we saw in theory, if you are storing a real value into integer, it will truncate to its nearest value. Let's see whether it is true or not. I want to display the I, so I'm copying this display function. Value of I is pi. So let's see what happens. I'm saving the code. There are no errors, so it is green. If there is any errors, it will be in red color. The right side corner, you can see. So I'm doing a behavioral simulation and it is done. See, the 3.14 is truncated to value 3. And as you can see, it is by default, if you don't specify any size of the integer, it is taking a size of 32-bit. So you can see the message also, the value of I is 3 and the value of pi is 3.14. Even though if you are printing in floating notation, since it is an integer, it was truncated to the nearest possible integer value. So let's do the same thing, but I want to assign I to some different value after, let's say, 100 nanoseconds delay. So this is a delay function. The hash trick will define it is a delay of how many nanoseconds? 100 nanoseconds. Even though this is not synthesizable, I was writing in the stimuli file, so it is okay to do the simulation. But these unsynthesizable codes like delay functions are not implementable. So I will explain what is that synthesizable code and non-synthesizable code in future slides. But right now, consider this as a delay element. The slash will define the amount of delay you want. In this case, I want a delay of 100. After 100 nanoseconds, I will do pi is equals to pi into 2. Let's see what happens to the value of I. I'm saving the code and running the simulation. So see, the value is truncated to 6 instead of 3, right? Initially it is 3. After 100 nanoseconds, you can see after 100, this is used to fit to the screen and this is used to zoom. After 100 nanoseconds, the value is changed to 6, right? So what happens if I add one more 100 nanoseconds delay? I'm copying the same code and I'm multiplying I with 4 times of pi and rerunning the same simulation. Now let's see, initially the value of I is 3, then the value of I becomes 6, then it became 13. At what time it became 13? You want to see the time also, so let's print time axis. At time is equals to, comma, there is a keyword called $time to print the time, comma, copying the same code. So let's see what happens. So at time t is equals to 0, it is 3. At time t is equal to 100, it is 2. Even though if you give 100 here and 100 here, it is adding this 100 to this 100, not executing at the same time. We want to see that, let's say 150. So what we think is this statement will execute at delay of 100 nanoseconds and this statement will execute at delay of 150 nanoseconds, but it is not correct. Since it is in always initial block, it will start executing this statement. After executing this statement, it will execute this statement. So it will add the 150 nanosecond delay to this 100 nanosecond delay. So the final delay will be 250 nanoseconds. This is very, very important. This will show that the flow is not concurrent but sequential in Verilog in our initial block. You can see the same thing here. At 100 nanoseconds, the value is 6. At 200, after 200 nanoseconds, not 200, we have added 100 plus 150. So after 250 nanoseconds, it went to value 13, which is represented by D. So this is the use of time variable, time keyword. So let's create one more example in which we will learn the different components of module. As we know, there are 5 different components inside the module that we have studied in theory. So let's see how to use them using an example. Let's create a project. In this particular project, I want to create that SR latch that I have explained in the theory. So I'm creating a SR latch project which is implemented by using 2 back-to-back NAND gates. So my module is SR latch. Okay, next, next, boards. I'm selecting gel board. Next, and finish. I want to close this. Since we have inputs and outputs, let's define them here. My inputs are S and R. My inputs are S and R. Since they are negation, SB I took, RB I took, and my outputs are Q and QB. So these two are outputs. So I'm selecting output. Okay. So now the Vivado will create the input output declarations like this automatically. Okay. Now you need to write the code here. Since the port declaration is done automatically, I am directly writing the hardware description where it was implemented using 2 NAND gates. The NAND is a function or keyword that is able to do the NAND operation in Verilog. So NAND output, comma 2 inputs SB, comma B, NAND of, I need to give a name also, right? This is N1 and this is N2. N2 QB, comma RB, comma Q, close semicolon, and module. So here the first thing is module name and port instant ports name, port list, and then this is instantiating the NAND module and this is AND module. So here we don't have any tasks and functions, so I'm not writing them, and we don't have any initial and always blocks also, so I'm not writing them. So this is my design source. In order to test this design source, I need to write a top module also. So that would be my simulation source. So how to add a simulation source? I need to click here and create a simulation source. Next, I need to create a source called top. I am creating a simulation source top in which I will call the design source. It doesn't have any input output ports, so I'm clicking yes. Okay. Now see, the simulation source has two sources. It doesn't know which one is top. Until I write the code of top, it doesn't know which one is top function and which one is leaf function. Top, in the top module, what I need to do? I need to call the, first of all, I need to define wires and registers. I'm defining wire out, comma out B as my outputs of the SR latch, and I'm defining reg set, comma reset as my inputs of SR latch. Now I need to call this function SR latch, not function, my module, design module, SR latch. I'm calling it with name SRL. You can give any name you want. In this, I need to call in the same order, right? The order we have defined is SB, RB, Q, QB. So same order you need to give. Set, which is negation of set, comma reset, which is negation of reset, because we are directly assigning SB here. So that's why I'm sending the negation of set, negation of set, negation of reset, comma. What is the next variable I have taken? Q and QB. So I'm assigning out, comma out B, close, and then semicolon. Let's give some inputs to it. So how to give the test vectors? I'm doing initial block, begin. I want to use a monitor function. We all know the definition of monitor function, right? It is different from display function. How it will be different? In the monitor function, whenever the variables or parameters that are defined will, if there is any change in the parameters that are defined inside the monitor function, then the monitor function will execute and show the values in the TCL console. So let's define a monitor function with time variable. I want to see at what time what is the values of set and reset. So I'm defining like this. My set is equals to percentage B, since it is a binary value, comma my reset is equals to again percentage B, comma my out is equals to again percentage B slash n. Slash n will define a new line, double quotes, comma I want variable set, comma reset, comma out, close, and semicolon. Now I will assign the values of set and reset. Set is equals to 0 initially, and then reset is equals to 1. I can define directly like this, or I can define one tick binary 0 and one tick binary 1. Both are same. As I have used semicolon, you don't need to write in the new line because semicolon itself will tell the line has ended. So I am writing both in the same line. After 10 nanosecond delay, I want to change the value of reset from 1 to 0, and again after 5 nanoseconds, I will change the value of set to 0 to 1. Let's see what will be the output. I'm saving this. Before saving, I need to write the end statement also to end this initial block. Now I'm saving this, and now you see the simulation file consists only one block, that is top block. Inside the top block, we have called this SR latch with name SRL. The same name appeared here. So this is the hierarchy that you can see. Top is the topmost block and SR latch is its leaf cell, right? So no mistakes. We'll run this, run simulation. We'll see the output. Okay, let's zoom here. Initially my set is 0 and reset is 1, right? Set is 0, reset is 1. At that time my output is 0 and output bar is 1 because I am resetting the SR latch. So output is becoming 0. After 5 nanoseconds, my set and reset are 0 and 1. So there is no change in output and output bar. Same values it is returning 0 and 1. After 15 nanoseconds, 10 plus 5 is 15. So after 15 nanoseconds, my set becomes 1. So my output will also become 1. So my output bar will become 0. So same thing you can see here using monitor function. See, initially at 0 time period, set is equals to 0, reset is equal to 1. So my output is 0. After 10 nanosecond, my set is equals to 0 and reset is equal to 0. So there is no change in output. After 15 nanoseconds, my set is equals to 1, my reset is equals to 0. So my output is set to 1. So this is an example to see the components inside the module. So here we'll see one more concept called port declaration. Right now we have declared based on the order, but uh, this is not a good way of declaring the ports, because let's say you forget the order and you have given reset first and set later, but in the main module you have defined set first and reset second. So let's see what happened. Since the Verilog doesn't know what is SB and set, it doesn't map SB to set automatically. You have to map by yourself. So what will happen? Let's see. See, even though my set is 0 and reset is equals to 1, my output became 1 because here I am passing reset value to the set value, right? So it is thinking this 1 is a set value, so it is assigned output as 1, which is wrong. So that's why it is always preferable to do port connection by naming like this. Dot, first of all, you need to call the variable from the leaf module, which is SB, and assign that variable to your variable. Here it is set. Set. You see, I am using the unary operator here, right? This is one example of using the unary operator. Again, I want to call the reset B and map it to my not of reset. Similarly, I want to call dot q from my leaf cell and map it to output, and dot qb and map it to my out b. So this is called port mapping, port mapping by using connect by name. Let's save this, run the simulation again. Now see the output. It is exactly what we wanted. Since set is equal to 0 and reset is equal to 1, my output is going to 0. This is the function of SR latch. So with this, we have shown different kind of operators that are existing in Verilog, and how to use module, and how to use a test bench to test the module, and how to give different test vectors, and how to use different uh, system tasks like dot monitor, dot time, and how to use data types like wire, register. We have covered almost all the basic concepts. Finally, I want to show one example in which I want to show you the hierarchy of the modules. For this, I am taking an example of ripple carry adder, which I have defined in theory. In this ripple carry adder, I will use 4 T flip-flops and I will connect them to give the output of ripple carry adder. Each T flip-flop I will make using D flip-flop and an inverter. So in this, I will follow a top-down approach and we will see the output by implementing it on Jetboard. Since this is a high level program, don't worry about the syntaxes and all. I will explain the syntax and all briefly in the coming sessions, like when I explain the modelings, different kind of modelings like gate level modeling, data flow modeling, or algorithmic or behavioral modeling. All the syntaxes will be explained there, but right now take it as an example to show the hierarchy of the modules. So let's begin by creating a project. Create project, new project. I want to create a project of ripple carry adder. In this project, this is an RTL project. I want to create a file of RCC, my ripple carry adder, RCA. Next, next. I want to choose a board, jet board. In this example, I will implement on jet board and show you the output also. Close this. We will define inputs later stage because I have already shown how to define the ports here, but I will write my ports in the code itself. So it has created a source file RCA. In this ripple carry adder, we will call 4 T flip-flops in which each T flip-flop was made by using D flip-flop and inverter. So let's start writing the code.